Okay, good morning, everyone. So it's my pleasure to introduce Ainhize Barrainkua. I don't know why I have to do the presentation because she's my PhD student, so that's weird. So she's going to present a paper that will be reacted in a couple of weeks, 3 weeks probably, related with uncertainty management in the field of fairness. It's a nice paper, and we hope that it will be accepted at some point in time, not too far. Okay, so go ahead.
Thank you very much, and welcome everyone. As Jose Antonio said, I am gonna present a work that is called Uncertainty Matters: Stable Conclusions Under Unstable Assessment of Fairness Results. And well, this work is a collaboration between Jose Antonio, Paula, Novi, and myself. So well, we all know that more and more high-stake applications, the decisions are being held by automated machine learning tools, and they have been shown to reproduce discriminating behaviors. So the effects of their predictions are disproportionate for different subgroups of the population, depending on the gender, on the race, or on the age of the groups. So, for example, it was shown that Amazon's job hiring tool discriminated against female candidates for software developer jobs, and it was due to the fact that the data they used was mainly consisted only like male applicants or male software developers. So it understood that something like gender would be a determinant to decide whether that person would apply for that job or not. Or also, Google's ad targeting offer higher paying jobs to male users than it did for a female user. So in the light of this issue, the machine learning community has come up with a lot of proposals to measure the fairness warranties of different automated machine learning tools, and also some interventions to increase the fairness warranties of those algorithms. So what is discrimination? Well, in the legal domain, there are two types of discrimination. And one type of discrimination is direct discrimination, and it's like intentionally harming or discriminating some individual because it belongs to a given group of the population, or because lying on some sensitive attribute like gender or the race of that person. And the second type of discrimination is indirect discrimination, and arises when under a seemingly neutral policy we are harming in a higher proportion some individuals of a group than we do for other groups. So it's like more a statistical viewpoint of discrimination. And how and why does discrimination arise in machine learning? Well, it can be due to lots of factors, but the main factors are listed here. So one is when we train classifiers in already biased datasets. So if we have any dataset that contains historical human biased decisions and we train the classifier to fit that data, it's going to inevitably reproduce that discrimination and even like amplify it. Also, if we've got some datasets that are not representative of the true population because we've got some missing data, or because we obtain those samples due to a selection bias or a sample bias, then they are discriminating. We are going to learn some populations better than others, and since it's not representative of the true population, then discrimination may arise in the target population. Also, it can arise because of algorithmic objectives. And for example, if we've got like an underrepresented group, and in most cases, algorithmic objectives involved improving the overall aggregated error, and it's gonna then learn better the majority group than the minority group, and therefore perform way better in the majority group and perform really badly in underrepresented minority groups. And so maybe someone would have thought up to this point that, okay, why don't you take away the sensitive information and make it blind to that information? Well, it's not that easy, because taking away the gender or the race of of an instance from the dataset doesn't improve, because sensitive information is also contained in the objective features. So there are many features that we think they are objective, but are highly correlated with the sensitive attributes and are highly predictive of those attributes. So it's not that easy as taking away the sensitive information, because we can still predict with high accuracy the sensitive information of the instances. And how do we measure the unfairness? Well, there are lots of notions and of very distinct nature, and they are mainly classified into two groups. Ones are individual notions of fairness, and the other ones are called statistical or group notions of fairness. So the former are based on the statement or the claim that similar individuals should be treated similarly. So if we've got two individuals or two instances that are similar, their outcomes should be similar also. So for example, here you can see, well, the probability of having a given outcome, it has to be smaller than a given epsilon if the distance or if two individuals are similar. And this is another elegant definition using Lipschitz continuity properties, and it's like this distance metric defined in this space, in the instance space, has to be, well, the distance of the outcome space has to be bounded by, upper bounded by the distance of the instance space. But the main problem of these notions is that we need to compare every two individual of the classifier, so it becomes really infeasible for really big data sets. And the other main issue is that we need to know this similarity metric, and it's not straightforward, not trivial to compute, because how do we know that two individuals are similar? Like, who defines that? And so many approaches assume that there is some group of experts, like an oracle, that knows this similarity metric, but it's one of the main obstacles of the practical use of these notions. So the community came, the machine learning community came with other kind of notions that are based on in comparing some statistical quantities over different groups, and they are way more efficient to implement and to use in practical purposes. And they can be grouped mainly into three groups depending on which is the statistical notion they compare. So there are notions based in the characteristic of independence that equalize some given acceptance rate, then also notions that require equality in the error rate, and also notions that require equality in the outcome frequency. So those that require independence means that the outcome should be independent of the sensitive information or the sensitive attribute. So here you can see two such notions, that one is a ratio and the other one is a difference, but it's mainly the same thing. So the probability of receiving a positive or a desired outcome should be equal for different subgroups of the population. But these notions are, well, the main problem they have is that if the prevalence is not equal across groups, then you might be giving positive outcomes to some instances at random just to satisfy this, but you are being unfair inside the group. So that's why they proposed other notions of fairness that take into account the real or the true class label of the instances. So one such notion, well, those notions are notions based in separation, which means that the outcome of the outcome should be independent of the sensitive attribute given the true class label. So those notions are, for example, equality of opportunity, which requires that the true positive rate is equal across subgroups. And equalized odds is like a more strict version, which requires equality not only in true positive rates, but also in false positive rates. And finally, we've got notions based in sufficiency, which means that the true class label needs to be independent of the sensitive information given the outcome. So two of such metrics are, for example, predictive parity that equalize the positive predictive value, or also notions such as equal calibration. So these three notions, based in sufficiency, separation, and independence, are at odds with each other, and they cannot be simultaneously satisfied if it's not under really trivial conditions. And also it's not clear which definition is best, so it's quite context dependent. So depending on which is your particular classification setting, then you choose one definition or another one. And one of the main issues that these statistical notions of fairness have is that when you are enforcing equality, you might be lowering or increasing the error of an easy to predict group instead of increasing or decreasing the error of the worst group. So what you do is basically enforce parity, but lowering a lot the overall error in the population. So that is not desirable, for example, in applications such as healthcare, where you don't want to harm anyone, so you don't want to make the predictions in an already good group worse. So in order to overcome that, some new fairness enhancing strategies were proposed, and basically what they aim for is lowering the worst case error. So basically they identify which is the worst group, and they try to improve the predictive performance of the classifier in that worst group. And well, now I'm going to talk a little bit about which are the main fairness enhancing interventions we can find. And there are many, many of them of really different nature, but they are mainly classified in three groups depending on in which step they enforce fairness. And they rely on different notions of fairness. So they can choose either an individual notion, a statistical notion, the min-max fairness, which is this one of improving the error of the worst group. And basically, in short, preprocessing algorithms transform the data that is fed to the algorithm so that when any conventional machine learning algorithm is trained in that data, it's going to output the output is going to be fair. So this can be done by, early approaches used resampling and reweighting, but new approaches aim to find a new representation of the data that is going to be fair. Then in-processing approaches modify algorithmic objectives so to account for fairness at training time. And this is usually done by either adding penalization terms because of unfairness in the objective function, or also adding constraints that enforce the classifier or guarantee that the classifier is going to satisfy some fairness notions. And finally, there are the post-processing approaches that modify the outputs of an algorithm so that the final predictions are fair. But these algorithms or these methods are quite suboptimal because fairness is enhanced in a really late stage of the procedure. So now I'm going to start talking a little bit more about what our work is about. So lots of, there were a couple of empirical results that suggested that the fairness metrics were highly sensitive to dataset composition. And in here, we performed a little experiments, and here you can see tenfold cross-validation results for different tenfold configurations for these fairness enhancing interventions. And as you can see, the results we get for different configurations are really, really different. So this means that the accuracy we get, and more precisely the fairness guarantees we get, have a huge variation. So how can we compare two algorithms fairly if their performance really varies with dataset composition? So we would need to make lots of repeats and compare them, but that becomes unfeasible for increasing dataset size. So we thought, we could modify the uncertainty of the results and explain this kind of behavior by assuming that the metrics were random variables. And there were some preliminary approaches that tried to do this, but they could only provide posterior distributions for one single metric at a time. But in fairness, you are comparing multiple objectives because you are on the one hand comparing predictive performance, but also fairness. So they couldn't be applied for like a multi-objective comparison of algorithms. And they also had another main limitation, and is that they could only be applied for holdout. Like in the cases where you have one training set and one test set. But in most of the cases, in the fairness literature, the algorithms are compared under the tenfold cross-validation or k-fold cross-validation. And it wasn't straightforward to apply to these cases because the results you get in each of the folds is correlated because you are using overlapping training instances. So it wasn't straightforward to know, okay, how can we apply this uncertainty? Do we average the posteriors? It wasn't that straightforward. So we proposed, one of the contributions of our work is to make this, this characterization also applicable for the k-fold cross-validation. So basically what we do is that we realize that, or the uncertainty we are modeling comes from the fact that when you want a classifier, when you want to evaluate a classifier in a given population, you don't know the real distribution of that population, and it's only observable through a finite set of samples. So you can only provide an approximation of the performance of that classifier evaluated in the samples. So we wanted to estimate the uncertainty we have regarding the performance of the classifier in the true population. So we start right from the beginning and model the uncertainty of the confusion matrix itself. Because if we model the uncertainty in the counts we get or on the number of correct and incorrect predictions we get, then by extension we can get the uncertainty of the performance metrics we are providing. So since this is since we want to apply it to a fairness-aware scenario, we choose one probabilistic model for the confusion matrix of each of the subgroups, so that we can also estimate the posterior distributions of the fairness metrics. And as I have said, since we consider a fairness-aware classification, we've got I've got the pointer. The objective or the non-sensitive features. S means the sensitive feature, and Y is the true class label. IID from the true distribution, which is unknown. And we want to derive the posterior or the uncertainty regarding the performance and fairness metrics. And performance metrics are functions of the confusion matrix. Not all of them, but most of them are functions of the confusion matrix, and we are going to concentrate in those. And fairness metrics are also can be described by functions of the group-wise confusion matrices. And our main purpose is deriving the joint posterior of a set of performance metrics and a set of fairness metrics for a multi-objective comparison. So what we do is basically assume that the counts or the elements of the confusion matrix are outcomes of a multinomial distribution where the elements of the confusion matrix sum up to the number of instances we've got of that particular group, and this is the multinomial parameter. And another assumption we make is that the multinomial parameter follows a Dirichlet distribution, and this is the prior. So by the Bayes rule, we can derive that the posterior distribution of the multinomial parameter can be written this way. So now this is like the base of the model, and then from here we compute the joint posterior distributions. So the joint posterior distributions cannot be obtained, in general they cannot be obtained in closed form, only for some very specific cases. For example, the notion of equality of odds that compare the true positive rates and the false positive rates. So those two notions, like equality in true positive rate and equality of false positive rate, account for different elements of the confusion matrix. And so those notions, those metrics are independent of each other. So they can actually be decomposed, like the joint posterior can be decomposed into the product of the marginals of each of the metrics. But this is not the general case where you compare, for example, accuracy with the equality of true positive rates or any other fairness metric. So I'm going to start with the holdout evaluation case, which is the most straightforward, and then I'm gonna explain what happens in the k-fold cross-validation. So as I have said, it's not the general rule that we can find a closed form solution for the joint posterior. So what we do is describe it by sampling. And how does the sampling procedure go? So, okay, imagine we've got a classifier and we've got a test set. So we feed the classifier with the test instances and we get some predictions and we get some confusion matrix, which would be this one. So for each subgroup, we obtain one confusion matrix. We obtain some counts. These counts are used to update the Dirichlet posterior of the multinomial parameter, which is this one. And we obtain one sample from the distribution. Then using that sample, we sample one instance from the multinomial distribution, from which we will obtain one sample of the possible confusion matrix, and then we compute the values of the set we define of the performance metrics and fairness metrics. And by this means, we obtain a set of samples that accurately describes the joint posterior distribution. But holdout is not the common practice in fairness, and we also wanted to make it applicable to k-fold cross-validation. But what happens here? When doing a k-fold cross-validation, each of the folds would provide one joint posterior. But the joint posterior are not independent. They are correlated because the models were trained in overlapping training data. So the most straightforward approach would be, okay, let's do a linear combination of this and account for the correlation. But it's not that easy and it's not straightforward. So the solution we propose is to consider an effective confusion matrix. And this effective confusion matrix contains the counts, the number of independent counts that are equivalent to the correlated results we get. And the effective confusion matrix can be, for each of the subgroups and for the whole population, can be described this way, where k is the number of folds we've got, and this rho is the correlation of consecutive folds. So if we know the correlation, we know k, so we can compute the effective confusion matrix, and then the procedure to obtain the joint posterior distribution is equivalent, but instead of using these numbers, we use the counts, the effective counts. But apart from that, everything is the same. But the main challenge here is, okay, and how do we know the correlation between consecutive folds? So there were some initial papers that proposed that the correlation was 1/k, but this is only true when the BC dimension of that algorithm is low compared to the dataset size, and also when in the case where the performance of the algorithm is robust with respect to different shifts in the data. And also other papers consider integrate this row or consider the row goes inside this range. But when we started doing it, we tried first with these ones, but what we realized is that, okay, it estimated well the uncertainty for some classifiers, but it did not for others. And that's why, because they assume that the complexity and the generalization ability is equal for all those classifiers, because we are considering the same row for every classifier. So that's why we came up with a new alternative to estimate row. And it's based in considering a reference algorithm from which we know the correlation. So for example, the correlation of the SVM is quite well characterized. So we can, for example, assume that our reference classifier is SVM, and then by knowing the row of SVM, we can estimate the row of another classifier. So this is done by this formula, and this R represents the difference in the variance in the estimated value over different k-folds. And this variance cannot be computed because it's unknown, and we consider an approximation for this R. So in the paper where they propose these estimations, they propose a method to overestimate the variance. So we assume that that overestimation is proportional for all the algorithms. Okay, so it's a huge overestimation of the variance, but it's proportional for all the algorithms. So the ratio of the variances is the same as the ratio of the overestimated variances. So that's how we estimate R, and since K is known because it's like the k-fold, we can compute the correlation of the results of different classifiers, assuming they've got different complexities and different generalization capabilities. And once we've got the set of the posterior distributions for different metrics, then now we can proceed with an uncertainty-aware comparison between two methods. So we can compute the performance gap, the uncertainty-aware performance gap, and fairness gap existing between two methods. So the first step would be computing the difference distribution, so the distribution that describes the performance and the fairness gap. And depending on where it lays, then we can make some conclusions. So the proportion of this delta that falls within this region is gonna describe the probability that one algorithm is better in all the objectives than the other. And likewise, if it falls, the proportion of the area that falls here. We also consider a region of practical equivalence, and is that region around the origin? Well, we think that those values can be considered as equal, so that it's negligibly different from the null value. And the dimensions of this region are described depending on which particular setting you are considering, but it's not really relevant because you can just, by providing this difference distribution, each one can choose which rope, or if it considers that rope is important or not. But it's quite it's a common practice in uncertainty when providing uncertainty-aware performance metrics, so we consider it also. And if we assume more dominance notions of algorithms from a multi-objective perspective, then the probability that algorithm A is better than B is the proportion of the area of delta that falls in this green region. And then we made some empirical evaluation of our method, and what we do is compare some frequentist results with the uncertainty-aware results and see what changes and why it changes. So we try to find a paper that contains a frequentist evaluation of a large range of methods, and it's this paper here. And we compare the results with our uncertainty-aware results. And we do so with the holdout evaluation, where we use the adult income data sets that has an already, it has got a train test split, a fixed train test split, and they use that split here. Then we see whether our approximation is really better than other raw approximations. And finally, we do the same thing as we did with the holdout evaluation, but with the tenfold cross-validation and the German credit dataset. So we compare our results with the frequentist results of this paper. So let's go with the holdout evaluation. Well, in this table, you can see the frequentist results obtained in their paper. So it seems that, well, they've got same accuracy, but the equality of opportunity, the value of the fairness metrics is way lower for A. So it seems that according to the frequentist results, A is better than B. But if we do a probabilistic assessment of the results and obtain, this is the delta distribution, the distribution of the performance and fairness gap, and we see that actually the probability that A outperforms B is 0.3. So the probability of observing that particular frequentist outcome or conclusion is only 0.3. Here you can see the posterior distributions in accuracy and equality of opportunity for both methods. And this cross marks the frequentist value. So as you can see, like frequentist value is just one random value, but you can actually get all these possible values for the evaluation. And then we also compare other two algorithms. This is the frequentist results they get. So here again, it seems that algorithm A is better because it's got a better accuracy and better equality of opportunity value. But actually, the probability of A outperforming B in all the objectives is 0.41. So actually, the probability of observing that particular outcome is way, way lower than 1. Then, well, we've got way more case studies, but basically the main idea is that, okay, when I consider a frequentist or an uncertainty-aware evaluation, then I get really different results. Then we also made some experiments to see whether our method to estimate the correlation was really better than those proposed earlier in the literature. And what we did is we considered different tenfold cross-validation splits. We made classification. We classified we made the corresponding evaluation, and we obtained lots of different points. And for each of those, we obtained the corresponding confusion matrix. So from one fold, we obtain one, like for one tenfold cross-validation, we obtain one effective confusion matrix, one posterior, and we compare whether the high density region is able to enclose all those points and whether it's narrow. So we want the posterior distribution to be able to cover all these points, but also we want to be as narrow as possible, because if we've got a huge posterior distribution, then okay, we will cover all the points, but it will be pointless because it will not give valuable information. And here we saw that the first two approaches are like, they provide almost 100% coverage. But as you can see here, for some methods, the coverage really lowers to 82% of the points. But our methods always like go around almost 100% of the coverage. So basically our method has got the highest coverage with the lowest area. So this method is the most certain to compute the uncertainty estimations. I forgot to tell you, but the difference between these two is that in this case, we assume that the reference is 1/k, and in this case, we assume the reference is in this area. So basically what we do is integrate between consider the row is between 0 and this value. Okay, so as I've said, our estimation of the correlation provides the most accurate uncertainty estimations. And then we compared the frequentist results of the reference paper and our results. So here again, in this case, it seems that method A has a better accuracy, since it has a better accuracy and better equality of opportunity, outperforms B. But as you can see, the probability of such event is only 0.3. And you can see here how the delta distribution is distributed. So it's quite, and it's basically the same conclusion, but you can see other two algorithms where A seems to be way, way, way better than B, according to the frequentist results, but actually the probability of A being greater than B is only 0.2. And something similar happens with this. So in here it seems that A is way better than B, but actually the probability of having such event is only 0.14. So we proposed an uncertainty-aware assessment of the results where you can compare multiple objectives simultaneously, and also that it can be used in many different evaluation scenarios. We are also able to perform an uncertainty-aware comparison between two methods and provide not only more informative, because you are giving the information about the probability of observing each of the possible outcomes of the comparison, and also those results are way more stable, because even if you use really, really different tenfold configurations, you get almost exactly the same posterior distribution. So the conclusions you draw from it, all the probabilities you get from there are really stable. Also, another interesting point is that it gives you the opportunity to be inconclusive, because in order to say A is better than B, you need to get a high probability of observing A better than B. But if you've got very little data, you don't get high probabilities of outcomes. Like all the outcomes are, okay, one is going to be maybe 0.4, another one 0.2, but there is no high probability in favor of one particular outcome. So in that case, you cannot make any decision of, okay, A is better than B. So by means of this framework, you can provide which is the probability of observing each outcome, and also say, okay, maybe in this case, I cannot make any conclusions. I cannot say A is better than B. I just need more data in order to be able to make such a statement. And that is only available if you consider uncertainty and you make such a probabilistic assessment of the results. Also, one of the main limitations or main critiques could be the effect of rope, because depending on which dimension you use for the rope, the results change slightly, because the change is not huge, but they can change some decimals. So it's basically up to the user or up to the setting you consider. You may not consider the rope, or we can just provide the delta, and each of us can consider the rope it considers that is suitable for the application. And well, this is not only applicable to compare algorithms, it can also be used to build new fairness enhancing interventions. Like at training time, you are considering the uncertainty of the performance of your classifier. And as future works, we will like to also extend it to other popular evaluation scenarios that are common in fairness, which are the Pareto front, like since fairness notions and the performance on the general predictive performance can be at odds sometimes, fairness results are sometimes provided by Pareto fronts. So we would like to be able to also compute those Pareto fronts, but taking into account the uncertainty. And well, thank you for coming, and if you've got any questions.
So, thank you, Ainhize. So it's time for questions. Roberto, ask a question.
So thank you for the presentation, great. And I'm not sure I understood every single detail, but in the validation at the end, when you compare the frequentist approach with the probabilistic one, then the question is, I understand that you may have or you may think of a different probabilistic framework, and then you could have like different probabilistic approaches. And if you consider then this example of the frequentist value for a single point, then in each of these probabilistic approaches, it may have a different probability.
Yes.
So
probably.
the question is, how can you, or to what extent is this probabilistic approach optimal? How can you measure or show this?
That's why we performed this experiment, and it's not easy to measure how good your probabilistic approach is in this case, and that's why we did this experiment. And basically our benchmark was computing lots of different tenfold cross validations and getting like 10,000 points and seeing if the posterior distribution computed for any random tenfold cross validation was able to cover all those points.
Okay. Now I understand the meaning. I'm trying to make it precise also around this area, right?
So yeah, we basically consider lots of frequentist results, and then we compute one posterior for each tenfold and see whether each of them is able to cover all these points. So since it's able, by doing just one tenfold cross validation, we can have the same information as doing lots of tenfold cross validations. Because even if you start from a given tenfold cross validation at random, it's always able to cover all the tenfold frequentist points that are possible.
Okay. And then a second question,
Yes.
Is it related, the classification problem have to be binary for the analysis, or can it be extended to?
It can be extended to multi-class, but then the definition of the confusion matrix is not that straightforward. But it can be extended, yes.
With the same probability, the multinomial one that you used?
I'm not too sure, I guess. I would have to think of that. But okay. Like we chose the binary because in most of the cases, in fairness, you've got like a desired outcome and an undesired outcome. It's mostly related to applications where you get hired to something or you get given a credit, or so there is some like desirable and non-desirable. So it's common practice to use, but yeah, it's definitely relevant to be able to apply it in multi-class. Yeah.
Thank you.
You're welcome.
And more questions from the audience or from the audience on? No. Okay.
Thank you for the presentation. It was really interesting. I have a question similar to what Roberto said about if you have like a multi-class setting, your confusion matrix will be like not 2 by 2, but C by C, being C the number of classes. But you are assuming like somehow not deterministic, but you are assuming that you are working on the predictions of the model, like the class predictions, but you are not working on the, let's assume a probabilistic model in the sense that it provides probabilities for each class. Is there any definition of the confusion matrix that takes these probabilities into account rather than?
No, I was thinking of it, yeah, some months ago I was thinking of that, like maybe if you give some probability of an outcome, so instead of having one count, you can have like 0.6 count here and 0.4 count here. So I was thinking kind of doing something like that. Well, we did the easiest thing and have not tried that, but yeah, I was thinking of doing something like that, yeah, but I have not tried it. No.
Do the definitions of the fairness metrics take into account, is there any probabilistic extension of the fairness metrics that take into account the probabilities of the classifier? Because maybe
Yes.
when you have like, I don't know, 0.6 versus 0.4 for a prediction, that's
Yeah,
something,
you can,
I mean, you are not being that unfair if you assign like a kind of uncertain answer for a...
Yeah. You can compare, for example, which are the scores that you are getting from, like if there is any mutual information between the probability you get and the sensitive information. Yeah, there are some measures that are like that. Yes, or compare the loss functions or the loss values for different subgroups and things like that. Yes.
And I have another question. In the very beginning, when you described the statistical notions of fairness and some fairness metrics like the sufficiency, etc., you said that all these metrics are at odds with each other. I mean that at odds. I mean.
Yes.
But is that sensible? I mean, what does it is because you are doing some kind of numeric approximation of an idea notion of fairness?
No, it's because of it arises mathematically.
Yeah, I mean, but does this make sense? I mean, why do you have like different notions of fairness and they are at odds with each other? I mean, does that correspond with an human notion of fairness? I mean, do we have uncorrelated or opposite notions of fairness in practice? Like,
yes, I think we do because because you describe it differently. So, because for example, for some, fairness was okay. Let's assume, for example, the easiest case is the one for calibration. So for some, being fair is okay. I need to be calibrated, and the calibration needs to be equal for all the groups. But for others, it was more related to outcomes. So yeah, I think we do have different notions of what fairness is, and sometimes, like, some people define the fairness notions that are more suitable for their tractability issues. So if, for example, they start by some notion, but they've got some tractability problems, and they describe a proxy, and yeah.
So it's not a problem of modeling the fairness in a mathematical way, but we also do have some.
Yeah.
Okay, I see. Okay, thank you.
You're welcome.
Okay, we have time for more questions. I was missing Iñaki.
Ainhize, I'm not able to ask you a specific question, but I was thinking that the pivotal point of all the work is that not assumption, but the umbrella of modeling the confusion matrix as a multinomial distribution. And I was thinking that several joint distributions are not possible. Some of them, I think so. Let's think, for example, in a domain where 20% of your samples are from one class, so the recall, the true positive of that class cannot be larger than 0.2, for example.
I know what you're saying, yeah, but you are...
I don't think that this has effects on your framework, but I was thinking about that.
Yeah, but the one thing is the number of people you have in the sample, like how many samples from each group you have, and how they are distributed, or how are they true class labels, as you have said. And the other thing is how the true population is really. So maybe according to the empirical population, you cannot have those numbers as you said, but maybe in the true population, you can have them. You don't get so different results, like you wouldn't get like a recall of 0.6, because like the multinomial parameter is really characterized by those counts. So it really like converges to almost the empirical value. It's close to the empirical value, but you assume as like uncertainty around the empirical values.
And then I need to say, in another slide further, I think that you show a proposal, this slide, to alleviate the overlap in the training faults of the scaffold, no?
Yes. This paper is original from, well, the idea was taken from an original paper of 2003, and it was in the frequentist assessment, and then we took it for the...
I was thinking that because years ago it was proposed, for example, an statistical test, a t-test based on course validation that did take into account this overlapping between the faults, and I don't remember exactly in which way it did alleviate this overlap between the faults, but sure that it was something similar.
Any suggestion is welcome, because we were like, and how do we combine the results? Like, do we average them? Do we not? And then we came up with this solution. But if you've got any suggestion that could be also useful, then it's very much welcome. Yeah.
This way of combining them is not so this way of combining them is not the most elegant from a probabilistic point of view, but it's what we could do. But from a probabilistic point of view, it's much more difficult. You have like a distribution for each of the faults. You have a confusion matrix that can be for each of the faults. That can be you have to consider as that comes from a probability distribution. So you should have to combine different distributions, and you don't know if they have the same distribution, so it's not that easy. It's not the best way to do it, but it's the only one we found. Well, Ainhize couldn't find better.
You either.
Ainhize, no, and just a last comment is that instead of a categorical, of a multinomial distribution, could it be possible to model the confusion matrix with a continuous distribution? I was thinking about that. Maybe like a Dirichlet. I don't know. It was
Dirichlet. But in the Dirichlet, the outcomes are between 0 and 1.
You can see also all the members in the confusion matrix, all of them.
Good.
No, I don't know if this can give you any advantage for the posterior work, but I was thinking about that. No, instead of working in the categorical space, maybe a continuous distribution, but just a comment.
It could be.
Who knows? Who knows?
I think we are over time. So if you want to ask more questions to Ainhize, she will be here for a while. So you can ask as many questions to her as you like. And just please join me. Thank you, Ainhize, for the presentation.
Thank you.